It's a long time no meet. Yeah.
Yeah, kids long time no see.
Yeah. It's a tough job.
So, Sean, whether the AMS setting has already been announced?
I don't think it be not announced because it posed to next year, then they still have time. Actually, to check this one. Yeah, I just checked this for 7 days ago. Yeah.
Okay. Yeah.
Yeah.
Hello, Huang Ting. How are you?
Good.
Yeah.
Okay, we almost start. We have 1 more minute to go. I will let all the participants to join now.
Yeah.
I can share my screen. Yeah. I'll see. Is it good?
Yeah.
Yes.
Good.
Is that in presentation mode? No. It's a presenter mode. You can see your next slide. Is that better now? Yes.
Yes. Yeah.
Okay, good. Anyway, I have this slide to show, so and then I'll go over to Professor Shaw.
Yeah, the similar pronunciation.
Recording in progress.
Okay, I guess we can start.
Sure.
Good morning, everyone. Welcome to the Scientific and Industry Webinar. My name is Song from CSIRO. And this webinar is co-hosted by AIC Energy Efficient Research Hub, Monarch Center for Member Innovation, and Member Society of Australasia. Firstly, I would like to acknowledge the traditional owners of various lands on which we are working today. I pay my respect to elders past, present, and emerging. So before we start, just a few simple housekeeping rules. And please mute your microphone while the webinar is on. And secondly, please post your questions on the comments using the chat function. So now it's my great pleasure to introduce our distinguished speaker today, Professor Lu Shao. Professor Shao is from the School of Chemistry and Chemical Engineering at Harbin Institute of Technology, China. He received his PhD from National University of Singapore in 2005. He is currently elected as a fellow of the Royal Society of Chemistry. And his research interests are membrane separation and synthesis fabrication of advanced functional materials towards environmental remediation and energy harvesting, such as carbon capture, water treatment, and hydrogen purification. He has more than 140 journal papers, over 6,600 citations, and H-index of 50. He currently serves as the editorial board member of the Journal of Membrane Science, editorial advisory board member of the ACS-EST Engineering, and also associate editor of Advanced Composite and Hybrid Materials. So now let's welcome Professor Shaw. So over to you, Professor Shaw. I'll stop sharing.
Okay, thank you. I will share my screen. So, can you see my screen now?
It's coming up. Not yet. Is Professor Shaw still online?
I think he dropped out. We
Yeah.
wait for a while for him to rejoin.
Not yet. Maybe now he has some background music now. Yeah, I think Professor Shaw must have some connection problem. Oh, he's coming back. Great.
Can you hear me now?
Yes.
Yes.
Yeah, there may be problem with my computer, and I use my laptop. I think it's better, but must there this one because there is problem with a sound for this one, and so the screen is okay?
Yes, very good.
Okay. Sorry for the interruption because of a network problem. And first of all, I will thanks Zhonglis for invitation, and thanks for Prof. Wang, Prof. Zhang, Prof. Shaw, and Sue's supporting for this webinar. Then I will go through my presentation, and the topic of my presentation is fabricating advanced membrane for molecular separations. Okay, I said here. And I'm Shanglu from Harbin Institute of Technology, China. This is my email, and you can check my updated work from my homepage. This is the outline of my presentation, include background, and I will talk about PO-based membranes for carbon capture and novel nanofiltration membranes based on artificial reactions for molecular separations and conclusions and perspectives. This is the background. Membrane separation have been widely used in the daily life and in the industry. Because membrane separation have the advantage of high selectivity and phase transition and less energy consumption, optimization and less oxidation. So there is somebody said that membrane technology played an important role in 21st century. I think the most important for membrane separation is currently is less energy consumption. From this paper published in Nature in 2016, we can see if we use membrane separation to replace the conventional separation process, such as distillation, then the energy saving may be up to 90%. One membrane separation has so energetic efficiency because it's street-powered separation process. It's different from the conventional equilibrium separation process because generally for most of membrane separation process there is no the mass phase transition because when the mass from one phase transfer to another phase during separation process, it will consume a lot of energy. For membrane separation, so it's no phase transition, then it's the most benefits for this one is energy efficiency. This is the different applications of membrane process. From here you can see membrane separation can be used for gas separation, proliferation, and nanofiltration, ultrafiltration, macrofiltration to separate the particle set from aromatic ionic range to the macro particle range. So it's very useful. My research work in fact focus on gas separation, nanofiltration, ultrafiltration, and macrofiltration. But for this talk, I only talk about the gas separation, nanofiltration, because it targets at the small molecular separations. So I will give a brief introduction on what's a membrane. A membrane is defined as a selective barrier that allows certain components in a mixture to pass through, but reject others, thus achieving a separation effect. Of course, for membrane separation, we must also to put some energy for the separation. So there is still a driving force for the transport. Driving force can be the pressure, temperature, also other driving force, but it can be classified as chemical potentials. So based on the driving force, we can get the flux. Flux is equal to K multiple the driving force. Then this figure shows the membrane separation process. We have a feed and transport through the membrane, achieving a separation effect. So what's the different membrane separation with lab scale filter paper? You can see from here. For filter paper, there is a wide process distribution, so it cannot achieve process separation effect. For the relatively larger process macrofiltration, the process may be around 0.45. Then there is a very sharp process distribution, so can achieve process separation. This is also another advantage for membrane separation with the high separation efficiency. So this figure shows my journey to separation membrane research. Just as I mainly focus on gas nanofiltration and ultra macrofiltration. Based on this, I think I focus on gradual evolution process of membranes because we consider gas separation membrane with the very small process which built by the free volume. Then for the nanofiltration, the pore size is 0.5 to 2 nanometer, and the larger pore size is ultrafiltration, and macrofiltration with pore size more than 2 nanometers. Of course, for this topic, we focus on bunker separation, focus on the pore size less than 2 nanometer. It's the gas separation membrane and nanofiltration membranes. So I will go through the first part, research part, and the PO-based membrane for carbon capture. We always know the carbon capture process, we call it CCUS, carbon dioxide capture, utilization, and storage. During CCUS, then the capture cost will account about 80%. I think it's between 17 to 80%. This figure shows the conventional combustion process. You can see from here, for post-combustion process, we must separate the carbon dioxide and nitrogen. For the pre-combustion process, we can target and separate the hydrogen and nitrogen. So the carbon capture is very important. Of course, there is the traditional carbon capture process by the PIC, TIC process, but I think membrane process is much more better for this separation because it costs a little. Of course, there is diversity of membrane materials for this kind of separation. We can use polymeric membrane. Polymeric membrane have such as ease of processability, affordable fabrication costs, and good performance. Also can use inorganic membrane and organic inorganic hybrid membrane, facility transport membrane. Currently, I think polymeric membrane is a very common material for industry applications. There is different kind of materials. The transportation mechanism of polymeric membrane for gas separation, we generally call it solution diffusion mechanism. It means that the feed gas will contact with one side of the membrane. By the interaction, we call it the solution process, then it be absorbed on the surface of the membrane. By the chain vibration, it can diffuse through the membrane and dissolve another set of the membrane to achieve a separation process. This is a solution diffusion process. During this, we can define the permeability. This permeability defined as the solubility multiple the diffusivity. It means that the permeability determined by the solubility and the diffusivity. And we also can achieve the separation effect. Its selectivity depends on the permeability of gas A over permeability of gas B. Also can be split into the solubility selectivity and the diffusivity selectivity. For the carbon capture, we focus on three gases. One is hydrogen, carbon dioxide, and nitrogen. Then this is kinetic diameter. Of course, hydrogen has the smallest kinetic diameter among these three, and later carbon dioxide 3.3 angstrom and nitrogen 3.64. Especially for carbon dioxide, their critical temperature is very high, like this 0.4 K. What's the CO2 selective polymeric membranes? Because if we want to develop CO2 selective membrane with enhanced separation characteristics, we must do the molecular design and modification of existing polymer. The CO2 selective means that, for example, we define the selective as a contributed by the solubility, selectivity, and diffusivity selectivity. For the solubility selectivity, it's determined by the thermodynamic factors. For the diffusivity selectivity, it depends on the kinetic diameter. Generally, if for CO2 and hydrogen separation, the glassy polymer generally is determined by the diffusivity selectivity. So it generally the hydrogen selective polymer. Then we focus on the solubility selective one as the determining factor to achieve a good polymeric gas separation membranes. So we can define it as CO2 selective membranes. It means that CO2 transports through the membrane much faster than we call them that. Then the CO2 selective membrane are dominated by the solubility selectivity. So this is different. Generally, if it dominated by the diffusivity selectivity is H2 selective. Dominated by the solubility selectivity is CO2 selective membranes. So what's the pros and cons for different membranes? You can see it's generally H2 selective membrane has some merits and limitation. I focus on the CO2 selective membrane. Generally, this kind of membrane may be mostly is rubbery materials, and it has merits such as pressurization gas may not pose a problem. According to our research, generally pressurization may be benefit for the not only on the probability but maybe on the selectivity. Also it has smaller membrane area required. Operational concern it may eliminating expensive H2 recompressions. So its energy saving is very good. Of course, for this kind of membrane, we also can use different materials such as rubbers, glassy polymer, carbon, xylate, and MOFs. Previously, my works mainly focused on this kind of membrane. It's PEO, polyethylene oxide. This kind of material have very simple structures. In fact, this kind of PEO, PG, commonly used for as bare materials for some applications in pharmaceutical biology, like so on. But we can use it for carbon dioxide capture because this kind of structure has a special interaction with carbon dioxide by the dipole quadrupole interactions. We call it the EO group. They interact with carbon dioxide. So we focus on that. But however, because this kind of polymer have very simple structure, it's easy to be crystallized. For example, for the semi-crystalline PO, it generally have very low probability, only around 12 barons. It's because this kind of semi-crystalline PO have the crystallinity maybe around more than 70 percentage. So for the crystalline part of this polymer membrane, it cannot pass through the gas. So the probability is very low because of the very high crystallinity for this polymer. So the researcher will do various work to improving the probability of this kind of polymer. Can be do it by modification of existing polymers, such as Lin Freeman's work to do the highly branched and cross-linked PO membrane, also do the PO blend membrane, cross-linked PO oligomer, and do the nanocomposites. Our work also based on the previous research. Okay, sorry. We developed, we call it forced impregnation strategy. In fact, we do two-step process to achieving a very good performance polymeric membranes for gas separation, especially for carbon capture. The first step is to use the PO600 monomer. This monomer has the animal functional group on the end and has the EO groups in the main chain. Also, it carries out this PO526 with and functional group for epoxy group and with chain with EO groups. So based on the animal epoxy reaction induced by the thermal method, we can achieve the network structure. This kind of network structure can greatly surprise the crystallization of PO to achieving the high permeability. But this is only the first step. Then we found this kind of PO network is very interesting because it can be swollen in water or in the ethanol. It means when the network swollen, then the small molecule may have the chance to go into the system to change the covalent structure. So we developed the second step to enhance the membrane performance. Then we put the small molecular PO, we call it PG, to dissolve in water. Then swollen the PO network membrane into the solution to put the PG into the networks of the membranes. We call it forced impregnation. Of course, we can use the ultrasonic to enhance the effect to impregnation. So let's see the results. This one is the original network membranes based on these reactions. Then for network membrane, then the permeability increased from 12 to 170. It also have a good improvement on the CO2 permeability increment. After impregnation, you can see we can do the different loading rate. They are around 50%. Then the CO2 permeability can be achieved with around 600 hours. So it's very surprising improvement for the permeability. Also, the selectivity almost kept constant, especially for CO2 over nitrogen selectivity. The selectivity also at the same time increased. It's very interesting. But we think it's not enough. We analyzed the system. We found that the ending of PG, the small molecular PG, has the hydroxy group. The hydroxy group will induce a strong hydrogen bond in the network, so it may also limit the faster transportation. So we replace the hydroxy group with methyl group, and then the permeability can increase a lot to around 1,000. Also, the selectivity almost kept the high values. When we replace two ends of the hydroxy group with methyl, then we can see the CO2 permeability can increase to 1,100 per hour. So it's very surprised, and the selectivity is still very high, especially for CO2 hydrogen selectivity. because the diffusivity factor, such structure and membrane have very flexible chain, also increase the free volume, can facilitate the diffusivity of the gas transport through the membranes. Also, it also can benefit the solubility because with such structure there is enhanced contact ion group. It has a better interaction with the carbon dioxide to increase the solubility of CO2 in the membranes. Of course, we do some work on the nanocomposites. We use the post to fabricate the nanocomposite of PU-based membranes, and found that the permeability is also good, more than 1,000 hours, and the interface is good because the post is functionalized. Also, we do some work on the mold to mix with PU to fabricate the mixed matrix membranes. For the mold work, we use UL66. We use two types of UL66. One is UL66 amino-functional one. Another one is the isopropyl functional one. We call it UL66 amine. That is different for our system because for our system we use UV crosslinks that this kind of functional group can react with UL66MA but cannot react with the amino group. So by this we use two kinds of UL66 to fabricate the PU-based composite membrane. We do the morphology checks. You can see for the amino-functional one, there is some defect on the interface between mold and PU. But for the MA one, because MA can react with the functional group during UV irradiation for the network formation, there is a better interface. You can see there is a very good interface. So we do the further test for the galactic transition temperature, also validating the results. The MA functional that has a better interface, and we do the test on the different mold loading to see, okay, for the MA one, there is a great improvement on the CO2 permeability compared with the amino-functional one. So we give the structure for the amino-functional one, there is poor interface. For the MA-functional one, there is very good interface for the benefit for the gas transportation and selectivity. We also do the AFM examination to verify this. I think most importantly, we do the different pressure to see the polarization effect on this kind of nanocomposites for the good interface and for the poor interface. From this, we can see for the crystalline one, it means that without any mold, there is when we increase the pressure from 1 to 10, then the CO2 permeability will increase about 12.9. If we have the poor interface increase much more than the pristine one, if it has good interface, then the polarization will be surprised. I think this is use this method is maybe a good strategy to illustrate whether the nanocomposite have good interface or poor interface by the polarization examination. Last part on this work, then we developed the semi-interpenetrating PU network. Because previous one we prepared the forced impregnation network, we must do the two-step. So for the loading rate, it's very difficult to be controlled. So we think how to control the loading rate to better modify the membrane structures. So we develop this work. This work is also very simple idea, and we still use the UV reactor monomers, the PEGMEA this one, and the PEGDA this one. Then we use the PEGDME as the penetrating molecular. The PEGDME has this kind of molecular structure. And one step UV irradiation we can form the semi-interpenetrating network. This is the membrane morphology, and we use different methods to characterize our already successfully synthesized this kind of membranes. Also, we examine the CO2 permeability. This red line is the permeability. You can see for the different composition, especially for this composition, the CO2 permeability achieving around 3,000 barrels is very surprising. As far as I know is the largest CO2 permeability for this kind of material up to now. The reason is similar to that one. We examine the diffusivity of gas and the solubility of gas. You can see from here, the diffusivity of CO2 increases a lot. At the same time, the solubility also increases a lot. I think for this kind of system, the diffusivity maybe increase more than 300, but for the selectivity, it only increase about 100. So the main effect of this system, the main reason for this system attribute to the diffusivity enhancements for these structures. Also, we do other tests to prove that the free volume increment and the whole structure may benefit to the CO2 completely enhancement. Also, we compare our work with the upper bound law. We found our membrane is especially good for the CO2 next-gen separations. So it over the traditional upper bound line. We published it in Anti-Environmental Science in 2017. Another part I want to talk is novel nanofiltration membranes based on the interfacial reaction for molecular separation. The generally used nanofiltration membrane can be asymmetric membrane or the composite membrane. The asymmetric membrane can be formed by phase inversion process. Then the material can be used by materials. For the composite membranes, we can fabricate the support membrane first and do the interfacial polymerization on the surface to fabricate the selective layers. Like this one, we do the interfacial polymerization. This process is used for industry fabrication process. Of course, we can calculate the flux of this kind of membrane by this equation, Poisson-Hagen equations. This one means that the porosity of the membrane, and R means the pore radius, and L means the length of the cylindrical pores. So based on this equation, we can see the membrane performance determined by the pore of the membrane, the selective layer pore. It means that the pore size and the pore distributions also depend by the thickness of the selective layer. Of course, thickness is smaller than the flux or permeance of the membrane is larger. But for the conventional interfacial polymerization, the reaction rate is very difficult to be controlled. It's predicted that the reaction rate between this value, then according to the Jack's report, then it has the reaction rate around 110. So we think whether we can use other methods to control the selective layer of the nanofiltration membranes. Previously, we do a lot of work on the TOPAWE and the PDA to modify the membrane, especially on the ultrafiltration membrane and the macrofiltration membrane, because the PDA is very sticky on the any surface. Also, PDA has the functional group and hydroxy group and amino group. It makes the membrane more hydrophilic. So we think about use the PDA simulated materials to do the nanofiltration membranes. So this work published in Journal of Material Chemistry A in 2020. We developed, we call it trinity coating to do the surface reaction for fabricating the very thin selective layer nanofiltration membrane. We use polyphenol and amino substance and some ice to do the reaction, because when we mix the three materials together to do surface coating, there is the interaction among them to do the better selective layer formation. From there you can see, in fact we examine the different systems. Because we examine the SOO PDA coating, we call it unary coating system. We also examine the binary coating system, such as PDA, PEI coating system. Also, we examine the ternary coating system, PDA, PEI, and ions. We think the COS is a better one. And you can see from here, for the PDA coating, the selective layer is more than 160 nanometer. For the binary coating, is more than 200 nanometer. But for the ternary coating system, it's very interesting, and it's only have 36 around nanometer. So it means that the very thin selective layer may benefits permeation of the nanofiltration membranes. Also, we examine the surface roughness, and that for the ternary coating, the surface roughness is the smallest one. This is the separation results. From here you can see for the permeance term and PDA, PEI, PDA, CO, and the ternary coating. For the ternary coating, it increased a lot compared with only PDA coating. So it means that this one is the best one. I think mainly because the very thin layer of selective layers, thin thickness. Also, this one ternary coating have very small water contact angle. It means that this kind of surface is very hydrophilic. We examine the process distribution and found that for the ternary coating band, it belongs to the loose nanofiltration membranes. Also, the surface is this one also with reactive negative surface charge. In fact, we examine the different ions
meta-analysis, we found that this has optimized in terms of probability and rejections. This is further examination on the selective layer thickness is around 30 to 40 nanometer. We verify the PI substance concentration and see the different effect and verify the coating tab because the coating tab will also affect the thickness. We found for the PI concentration is around 0.6 and the coating tab around 6 hours if we can get achieving the best results. The permeance is around 114 and the selectivity around 100 is very good membrane. And we examine the separation efficiency for this membrane for different dyes. From that, for the CV dyes, there is very low rejections. For other dyes, have very high rejections. Also, we examine whether the dye absorbs on the surface of the membranes. We found the dye absorption is very small. It generally less than 2%. Finally, we compare our work with some others' work. You can see for our work we have very high permeance, also very high selectivity. Much higher than other work we can refer to. The membrane also have good anti-folding performance, also have very good stability. I think because of time shrinkage, I will talk about the last part of our recent work. We work on the COF membranes. The COF membrane for nanofiltration can be fabricated by the different methods such as in situ growth and artificial polymerization that makes the COF into the reaction solutions. But in our work, we developed we call it molecularly soldered COF membranes. This COF membrane is very unique because this kind of membrane fabricated such as PA mixed with DA monomers. During this process, we add DA during the formation of the COF crystalline on the porous support of membranes. The DA can induce some we call it reactive oxygen species. This kind of ROS can accelerate the nucleation of COF, so to promote better COF membranes. At the same time, the DA on the surface decoration of COF can increase the COF membrane hydrophilicity. Also, because the DA is very sticky, then it can be used as materials to molecularly solder the COF membrane to make it very strong and stable. Then we do the density functional theory calculation to simulate the process to find if we have DA involved in the formation of COF, there is a much smaller anti-barrier for the COF formation. It means that such as the reactive oxygen species can facilitate the nucleation of COF. Also, we do some other tests. I think during this process, the most important is what kind of solvent we use. We test different solvents. such as we use pure water and pure ethanol. Also, we use mixed solvent of water and ethanol. We think the mixed solvent is the best because you can see when we use pure water, we use the pure water, the permeance is very low, although the rejection is high. But we use pure ethanol, the permeance is high, but the rejection is very low. When we use the mixed solvent, water and ethanol, then we can achieve a high permeance and high rejection. We think this is due to when we use the mixed solvent, it's better for the loss, facilitate to the nuclearization of the COF membranes. But for the another two systems use pure water and pure ethanol, there is a big benefit for this process. You can go through the detail on our paper published in Science Advances for this process examination. And we also show the different membrane morphologies when we use different solvent. We found for the mixed solvent is the best one. And we examine the structure of different membrane in terms of chemical structure and physical structures, and to prove our membrane is formed successfully. And this is the performance for our membrane for desalination. From here, you can see when we only use PDAPA or TAPA pure COF, its performance is not so good. When we use PDA and TAPA, it means that PDA modifies the COF, or we call it molecular soldered COF. Then we have the best one, the high permeance and high selectivity, especially for NaSO4 separations. It's good for the desalination and the loose nanofiltration membrane. Similarly, we also compare our work with other work, show our membrane is good. In fact, because the COF membrane generally is weak, have weak interactions, so it generally cannot be used for organic solvent separations. But because our membrane induces the Da2 molecular soldered the COF crystally, and it has very stable structures, can be used in organic solvent separations. So even though it do the organic solvent separation, it still have very high permeance and very high rejections. Also, because of the modification, there is good hydrophilicity, and so it has good anti-pollution ability. We also test the stability of our membrane, show our membrane is very stable in terms of the separation performance. Also, it has increased mechanical strength, and the thermal stability is also good. So this is the conclusion. I think due to the micro-separation characteristic of nanofiltration membrane, the engineering, the selective layer is very important. So we must discover the nanoscale thickness. It means have very thin thickness. Selective layer. Also, this kind of layer must have very stable structure for the separation. Also, this kind of layer have very good interface with supporting membranes for the practical usage. For gas membrane, I think it's the most challenge. The new material must be discovered, especially for the solution diffusion mechanism. Okay, last part I will thank all of my colleagues, including Prof. Xie Wang and in Australia. Also welcome you visit China, Harbin in the winter. Okay.
you, Professor Shaw, for the excellent presentation. It covers a lot of new membrane development from gas separation and also like nanofiltration. Now it's question time. Maybe I'll start now. And I know like say material development for the polymeric membrane towards the CO2 separation. So I want to get your comments like what would be the biggest challenge to utilize polymeric membrane towards practical application for CO2 separation?
I think it's a good question because sometimes we have developed a lot of PO-based membrane for CO2 separation, but it's only developed on the lab scale. I think many companies interested in our materials, but for this kind of material be used for the industrial application, must be overcome some difficulties, such as our material may be for use for the, for example, syngas process. It must be very robust, such as it have can bear with high temperature and can be very have better good mechanical properties for applications. Currently, our PO-based membrane, the mechanical property may be a problem. So this is our future work to do some work to improve the mechanical properties. Also, we can develop other materials to do the carbon capture. In fact, such as we do the PIM, polymer intrinsic microporosity, PIM membrane to do the carbon capture. But although the PIM have very high permeability for CO2, but the stability may be an issue. So we must balance the membrane advantage and disadvantage to be suitable for the practical usage, especially considering the practical industry process conditions such as temperature, pressure, and what kind of other contaminant maybe also have a negative effect on the membrane performance, especially for the long-term performance. Okay, thank you.
Thank you for that insight. We have a question from Ming Yong, and the question they want to ask directly, you want to read it out. Ming, are you there? Let me read out. And the question is like how does the PDAP cover the ternary membranes achieve high rejection towards violent ions? Is that due to the accelerated polymerization or the narrow size distribution?
I think it's a good question. I will show. Let's see. I will show this one. Because we also want to investigate the real mechanism. We use polyphenol as one materials and use amino substance because generally use PEI to do the system formation. In fact, we also use transition metal as another term of material. Use this one, and the polyphenol to do the trinity coating. Generally, for previously, the researcher have used one materials or two materials, such as use only PDA or use PDA PI, or only use PDA and transition metal as. But I think for the ternary system, for the three materials interact with others, So it supplies the interaction between two materials. So during the suppression, then the reaction will be retarded. Because of retarded formation of the membrane, so the very thin membrane layer can be formed with very good pore distribution. I think this may be the reason, but in fact we want to further do the simulation on this process. But because the system is very complicated, this cannot be do the simulation. We search other groups to help us to do that. But I think the main reason because the competition between the three materials to suppress the membrane formation process to obtain the very thin layer of selective layer with very good pore distribution. Okay.
Thank you.
Thank you. I think, we're kind of the time. So I think probably still the question time now. I want to come to this stuff and if you want to discuss offline. And so, before we finish, I'd like to thank for this excellent presentation today. And also I want to thank all your participation for the webinar as well. And I'd like to share one slide.